surface, but also you have to consider the bulk material and the property chemistry altogether. So surface composition is very important for the implant, specifically for alumina, zirconia, even the most of the metallic implants, because there it doesn't interact much with the water other than the surface. So only mostly they interact only on the surface, and surface roughness is very important. Surface roughness is also very important. Some of the surface roughness can cause activation of the macrophage activities. That is also, it's not desirable. So surface topography is important. So mostly when we augment this implant into the body, firstly the water molecule will interact, or body fluid will interact with the material, as well as the protein start absorbing on the material surface, and protein also may denature, and eventually once the protein is absorbed on the material surface, the cell will adhere on the surface of the protein, and then eventually cells start proliferating, then migrating, and if the surface provides specific cues or specific what you call conducive environment, then cell also can differentiate into specific lineage. If I am going for cartilage application, the stem cells can differentiate into chondrocyte. If we are considering the bone, the cell can differentiate into bone cell lineage like osteoblast, and also if we are considering the skin, it can go into fibroblast or keratinocyte. So that is essentially nowadays done by delivery of growth factors, but actually the surface or the surface chemistry can also be tailored in a way that it can help in differentiation, and of course after differentiation cell will synthesize the tissue specific extracellular matrix. This extracellular matrix deposit on the surface of the material, and eventually more cell interaction will start. Okay, and in case of bone application, definitely we want the calcification. That is the primary requirement. Okay, so once the implant is augmented into the body, the first thing is the protein. First thing is the body fluid interact, and body fluid contains huge amount of protein. The protein also start adsorbing on the surface, but actually it depends on the material surface. If the material is hygroscopic, if material is hydrogel type materials, so after augmentation it actually takes a lot of water and it swells. So there will be competition between the proteins as well as the water. So we want protein or we want water. So there will be competition. Of course we want the protein, but we don't want any undesirable proteins. We want the proteins which is responsible for specific cell adhesion. So that is the most desirable. So that is why you will see that in such study, most of the studies, the first they do a lot of protein adsorption studies. That is very important. So now proteins are very complex molecule, and it has a primary, tertiary, quaternary structure, and interestingly, depending on the polarity, depending on the environment, it changes its three-dimensional structure. Okay, so if the surface is hydrophobic, the hydrophilic surface will be hidden inside, and the polar surface will be inside, and the hydrophobic surface will be outside. But if the environment is highly hydrophilic, the hydrophilic surface will be exposed outer world, and the hydrophobic surface will be inside. It's clear, right? Similarly, so there, if the implant is hydrophobic or hydrophilic, whatever it is, so there would be hydrophobic interactions, hydrophilic interactions, as well as hydrophilic interactions. Eventually, hydrophobic interactions like the hydrophilic interactions, and hydrophobic interactions like the hydrophobic interactions. If the material surface is hydrophobic, then eventually water is not able to adhere to the surface of the implant because it is hydrophobic, and eventually protein, and there will be very sharp margin between the body fluid and the implant, and the proteins which are approaching this border of the body fluid, and they actually hydrophobic surface will be exposed, and gradually they percolate through, and then they adhere to the surface of the implant, and that is how we can have wanted protein adsorption on the material surface. But eventually, which surface is the most favorable? it's very difficult to say whether it is hydrophobic, hydrophilic, or it is in between hydrophilic and hydrophobic. Of course, it is in between the hydrophilic and hydrophobic. Okay, so that is important. So we need to have desired protein adsorption on the surface of the material, and of course we should not have too much hydrophobic surface, but we should have the surface which is favorable for specific protein adsorption, not the non-specific protein adsorption. And for protein adsorption, there is an effect called Frohman effect. That is also very, very important. That we see that when proteins are trying to adsorb on the surface, it is a highly reversible process. And first of all, as we know that small molecules, as we know the Brownian motion, it directly depends on the mass. So smaller molecule move much faster. So initially the small molecule will adsorb on the surface, but with time the materials or the proteins or the molecules which are having much favorable bonding and stabilization, those molecules will go to the surface and will adsorb. Okay, and then that is eventually forming the stronger bond. So it gradually replaces the small molecule, and so it is one of the example that the blood, where fibrin, which is usually abundant to bind to the surface first, and over the time it replaced with a larger protein. Okay. Then cell adhesion. So that is also important. When we have the material like whether it is titanium or alumina or bioglass or polymers, anything you have, now we know that the materials after augmentation, right? There is a competition between the proteins and water, and once the proteins are able to adsorb, now it is the turn for the cells. So cells will come in and it's trying to adsorb or adhere on the surface of the material. So does it adhere on the surface of the material? It can, but it depends on the charge of the surface, and also it depends on the type of protein it is adsorbed. If the protein which is there, which is favorable for the cells, so cell surface has a specific protein molecule called integrin. Integrin is a cell surface protein or receptor which adhere to the surface of the which usually adhere to the surface of any material. So if a material which is augmented into the body, it adsorbs some protein like collagen. So collagen has a cues called RGD, arginine, glycine, and aspartic acid. Okay, these RGD cues will be immediately recognized by the cell surface receptor called integrin, and they binds. And this binding is essential for focal adhesion of the cells. So once the cells will be adhering on the surface of the material through focal adhesion, you can see in the next slide that this F-actin filament will be stretched. F-actin filament will be stretched, and eventually that will promote different cell activity related cascade and activation of cell activity related cascade, and that eventually helps in synthesis of different protein synthesis will be activated. So as you see that here in case of F-actin, which is bound to the vinculin, and this vinculin also bound to the tallinn, and this tallinn is bound to the integrin, and this integrin is actually binds to the molecule by focal adhesion, and focal adhesion is very, very important. Okay, so when cells are adhering to the material surface, it is through focal adhesion, it is through integrin receptor, and when cells are adhering to the cells, it is through weak adherent junction. Okay, so cells when adhering to the cells is by weak adherent junction, when cells are adhering to the material is by integrin receptor, and most importantly, usually when the body fluids are interacting with the materials, this material has the protein which adsorb to the material surface, actually cells are binding to the protein side. That is very, very important to know. So cells are actually adhering to the protein surface. So one of the example is collagen 1, which has a RGD cues. Even silk has a RGD cues. So this cell surface integrin will adhere to the surface of this material. And interestingly, this cell surface has highly negative charge. So cell, that I think I will come shortly. And so if the material surface, if you can make highly positively charged material surface, then this negatively charged surface of the cells can adhere to the surface of the material, and that eventually is desirable. But at the same time, if the cells are too firmly attached to the material surface, it will impair the cell migration. So that is why you need to have a balance between these two. Okay. So now once we have the material, we need to do the testing. That is obvious, right? So whether it is polymers or it is ceramics or it is metal, but we need to go for testing, whether it is suitable for biological application or not. So first you have the raw materials, we go for chemical testing, we go for physical testing. Like if you are going for load bearing applications, whether it will be able to withstand that load, whether it will be able to uh, to sustain that many cycles of loading and unloading, so that it should not have fatigue failure. Similarly, the chemicals which is composed of the specific material is, so this chemicals, if it is exposed to the body fluid, whether it will have any undesirable consequence. So similarly also biological response. So we need to do the chemical testing, we need to do the physical testing, physico-mechanical testing, also we need to do the biological testing. And of course we need to do the biocompatibility study, like cytotoxicity. So whether the cells, if it is adhering on the material surface, they are dying or not, or if they can adhere to the surface, how many or quantitatively how many cells can adhere and can proliferate and differentiate or migrate. So all these activities you need to see. And similarly you need to see the kind of whether it has any irritation activity or systemic toxicity, hemocompatibility, even carcinogenicity if it is there. You need to test all these. So product and process validation. So when you are making the implant or the materials, so you need to see the environmental aspects, and also manufacturing sterility. As I mentioned that ethylene oxide is used for sterilization. So if there is any residual ethylene oxide, that can also cause toxicity. So the finished product qualification. So the finished product, whether this finished product can be utilized for the specific intended application. And of course routine testing. So you need to do the periodic auditing and testing of the implant while it is in the manufacturing side, and also you need to do the some kind of release testing. So there are two type of tests usually we do in our laboratory. One is called in vitro testing. So in vitro testing is actually, in vitro meaning what? In vitro meaning in glass. Okay, so it is done in rapid and it is quite inexpensive. It is not inexpensive, I should say, in terms of Indian context, I should say, and it's a need huge amount of money anyway. It's very I mean, this kind of activity you need a lot of money, and then poor representation of physiological condition, because basically you are taking specific cells and then you are doing the testing, but actually when implant is inside the body, there is a local response as well as there is a systemic response. So we are not considering the systemic response. So that is why it is a very poor representation of physiological condition. And similarly, it is a good step to start with. And I think if you recent time, if you see the literatures, some countries, I should not name the country, but they are, instead of doing even in vitro testing or even animal testing, directly they are going for human testing. That is too dangerous. You should not do that. First we should go for in vitro testing, then you should go for animal testing, and based on the result of animal testing you should go for clinical trial, and then it should come to the market. So easily it takes more than 20 years. So that is why you need to think before whether you should come to this field or not. So it takes very long time, and eventually if after 20 years you come to know it has some problem, it's totally disaster. You spend your life, but finally so that is why you need to very careful when you need to very when you are going for such type of materials for the specific application, and we need to make sure that I'm convinced it will work. And we need to do, you have to be very, very rigorous about all the testing, and then you should come to the next stage. So of course animal trial is important. Whether you go for in vitro testing by stem cells, you need to have ethical clearance. Even similarly, if you are going for in vivo testing, it also needs ethical clearance. And so it is very, very important. Without ethical clearance, we should not do any such kind of testing, and it takes time. I can tell you couple of ethical clearance still pending with institute more than 3 years now. It takes time because they are I mean there are different issues, so we have to continuously, we are learning with the interaction, and then how this there could be some error and all, so we need to follow all the protocols, and then once it is clear, then we should go for animal testing. Okay, so but it is a better approximation to the human environment. For example, if you are going for teeth, I think somebody was talking about the teeth. So if you are going for testing of the teeth, right, so you need to see very similar chewing and loading kind of simulation is possible with the animal, so you should go for that kind of animal testing. So for example, pigs is a very good model for dentures, right? Similarly, hip, I think horse is one of the good model, even dog is a good model for hip. And so when you are going for animal testing, we need to go for animals which is very suitable to the specific specific condition. So demanding protocols, we need to go through the protocols, and we need to choose the right animal model with approximate human environment, and it is a second step prior to the clinical use. It is a second step prior to the clinical use. So in vitro testing, and of course we need to go for cell culture. So here what we do here, we collect the tissues from different sources, and again, as you are collecting the tissues from animal or human, you need to go for ethical clearance. It is obvious. So once you collect the tissues, you basically dissect the tissues, chop into small pieces, then you digest the ECM, and then so you place them in the petri dish for culture. So once you place them in the petri dish for culture, you follow up the culture, and you see that cells are adhering to the petri dish, and then they are expanding, and they are taking very desirable morphology, then it is suitable for use it for different testing purposes. But interestingly, you will think that the cells were there in the tissue, they are in the 3D environment. When you are culturing it, it is actually in the 2D environment. Once it is in the 2D environment, so it may lose their phenotype, it may lose their properties. So that is also you need to consider. Nowadays, a lot of companies are introducing many different type of products for 3D cell culture. It's a very recent development. You can see every alternate day there will be 5 patents from different companies. One is Matrigel. Similarly, you see 3D petri dish, for example, hanging drop methods. So I think I have it, I can show you. So this is I think this is one of the product which is patented in 2012, I think, and it was displayed in China conference. I have taken it from that. So you see, it is basically a drop while you are doing the cell culture. It actually I think it's not very clear. So you can see there are small well plates, and these small wells where the drops are hanging, and the cells are actually cultured in that. Cells can take 3D geometry. Cells can take 3D geometry. So it is very, very important to maintain the cell properties. So in vivo testing, so that is, of course, it is important. So critical for development of clinical devices. So in vitro testing cannot replace the in vivo test anyway. So it should not have any inflammatory response, it should not have any immune response. So here, in case of in vitro testing, you use single cell type, but in case of in vivo testing, we can see the systemic response, and no tissue remodeling is possible in case of in vitro testing, whereas in case of in vivo testing, so we can observe the tissue remodeling. It also has hormonal effects, and many different type of cells can interact with the implants, and also it interacts with the blood-borne cells, proteins, molecules, and of course finally you see the systemic response. This is very, very important. So there could be irritation because of the materials or leaching of the chemicals from the materials. That could cause inflammation like redness, swelling, heat or pain. I think the surgeon can easily suggest, right? So similarly, the chemical additives, processing, manufacturing aids are also important, like detergents are used. Ethylene oxide, as I said, residues are used for sterilization, or there could be any inadvertent contaminations. Okay, so that also can cause a problem. So you need to be concerned about all these. And of course, as I mentioned, that if you are going for animal testing, we need to go for committee for, you need to have a clearance from the committee for the purpose of control and supervision on experimentation on animals. Similarly, if you are going for stem cells, there are guidelines from Stem Cell Research India, NAC, and also there are guidelines from institutional ethical clearance for animal as well as for stem cells. And also if you are going for the product development, we need to get the approval from DCGI, Drug Administration of India. You need to have approval. Unless you have approval, so you should not go for human trial. And once it is approved by the DCGI, then only products can be reached to the market. And interestingly, I think today DCGI of India is not yet well defined, and drugs and implants all are come under the same category. So we need to work, I think, together still to define the what is a drug and what is the implant, and we need to make more what you call stringent protocol for that. BSI is one of the I think standard for SOP, standard operating procedure. If you are manufacturing a product, then you need to go for BSI certification. Very, very important, because the materials or the product which you are manufacturing, whether you are following SOP or not, that is very important. And also you need the clearance. CE marking is also important if you have to market this product in the European market. FDA is a Food Drug Administration of US. That is important for clearance. And interestingly, we should mention, usually FDA approve not the material but the product. Why? Because the material could be non-toxic, but the process you are using for manufacturing may be toxic. So that is why FDA approval should be done for the process and the final product. For example, if I am using a material, I am dissolving in water and I am making the product out of it, it may not be toxic. But the same material, if I am dissolving in trifluoroacetic acid and making the product, it may have some remnant trifluoroacetic acid which is very toxic to the bodies. And if FDA approve this product, which is developed by this water-based thing, and if it is trifluoroacetic acid based, it will release the toxic chemicals. That is why FDA will approve the specific product by the specific process. Okay, that is you should consider very carefully. And ASTM standard, as you know, that it is very, very essential for any of the products. Okay, so then we come into the subject now, bio-inert implant and bioactive implant. But here I would like to say that there are, of course, bio-inert material and bioactive material. So bio-inert material are the material which are not recognized by the body, which are recognized by the body. But eventually, as we know, that it's recognized as a foreign body. And then what happens? The higher fibroblast activities and eventually fibrous encapsulation all around the implants, right? And bioactive implants are the implants which are recognized by the body. So there are two types of bioactivities, I think I'll tell shortly. One is for heart tissue implant, we consider the bioactivity meaning the implants which can grow inside the body, okay, which can grow inside the body. And in another case, I'll say that the implant surface will have specific cues like RGD, YIGSR, and those bioactive small peptide cues that will be recognized by the cells, and cell can actively adhere to the surface, or also protein can recognize those. Okay, clear? So here I would like to say osteoconduction. Osteoconduction is a study which is introduced by Kokobu. Okay, and it says that I think SBF was introduced by Kokobu. Its osteoconduction was suggested by Wilson Henge. It says that osteoconduction surface is one that permits the bone growth on the surface or down to the pores or to the channels or the pipes, but it's not fully defined yet. And so osteoconduction is the term means the primitive undifferentiated or pluripotent cells are somehow simulated to develop into the bone forming cell lineage. Sorry, it is a osteoinduction. Sorry, osteoinduction is the term which is primitive undifferentiated or pluripotent cells somehow stimulated to develop into bone forming cell lineage. So osteoinduction is the process where the primary cells or the pluripotent cells can be differentiated into bone cell lineage. So that is also called osteogenesis. That is called osteoinduction. And osteoconduction is the process where the materials will grow while it is augmented into the body. Okay, so we should do some kind of surface modifications. We should do, or we should have some chemistry on the surface of the material that helps for the growth of the bone. That is osteoconduction. So what we can see here is different type of simulated body fluids are available for different type of testing. One is called human blood plasma. We see that different concentrations of sodium, potassium, magnesium, chloride, carbonate, phosphate, and sulfates. Similarly, we see the SBF. SBF was introduced by Kokobu, simulated body fluid. So it has slight difference in terms of different ions concentration. As we can see here, sodium is very similar, potassium is also very similar, and what you can see, carbonate has some difference, and chloride also has some difference. Similarly, Ringer solutions, we know the Ringer solutions, we also know the Hank solutions, so there is some difference in terms of ions concentration. So these are used for different type of characterization of the biomaterials, for simulation studies, etc. in vitro. So those simulated body fluid was introduced by Kokobu, but actually if you see the simulated body fluid, they have both calcium and phosphate. We know the calcium and phosphate doesn't stay together, it actually precipitates out. But actually in body, that at specific physiological condition, at specific pH and temperature, this calcium and phosphate stays together, it doesn't precipitate out. So this is a kind of metastable condition. And you can see here very different type of simulated body fluid was developed at different course of time, but finally you see that the final composition which was proposed by Kokobu is by this method, where we have a separate calcium solution, separate phosphate based solution, and once you make the separate phosphate based solution and calcium based solution, you mix together at 37 degrees centigrade at pH 7. At room temperature also you can make, but at pH 7.4 using Hibbs buffer, and it doesn't precipitate out. And these solutions can be used for different type of osteoconduction study in vitro. And this simulated body fluid can also be used at for biomineralization studies. For example, very different groups has introduced n different types of simulated body fluid. They have used 2 times simulated body fluid, the concentration is double, 5 times, 10 times to accelerate the biomineralization in vitro. Is it clear to all of you? So this is one of the study I think we have done back in 2004. So this is a PCl, polycaprolactam is a polymer, which is having very surface, very smooth, I mean not very smooth, its surface is smooth, and then once we do some kind of sodium hydroxide treatment we see that there is a rough surface on the surface, on the PCL surface. Actually, the PCL is a polycaprolactam, which is a amide or ester. If it is lactone, it is a ester. If it is lactam, it is a amide. So these materials are actually amide or esters. So they are, if it is hydrolyzed with sodium hydroxide, they actually break down. This amide or ester bond breakdown eventually introduces a lot of carboxylic group and amine groups. This amine and carboxylic group introduction and breakdown causes surface roughness, and this actually acts like a nucleation site. This acts like a nucleation site. So what we can see now, if we dip this into simulated body fluid, what you can see on the surface of the material in the laboratory, we can grow like a bone. That is very interesting. And so you can see that this surface, I think this was done for 30 days. So with 30 days, we can see very nice bone growth, bone-like morphological growth in vitro. Okay, in vitro using SBF, simulated body fluid. So as you can see by FTIR studies, Fourier transform infrared spectroscopic studies, that you can see that sodium surface after treatment with sodium hydroxide, there is a increase in carboxylic carbonyl group, and then when it is treated with phosphate and calcium bath, we can see there is a higher activity of phosphate, and then this phosphate, when it is dipped into simulated body fluid, they grow and they form a layer of bone-like morphology. Similarly, this PCL fiber, when we make the nanofibers by electrospinning, it's very interesting to note that it is within week, but I can we also did the study, because it has nanofiber, huge surface area, these nanofibers can have bone-like growth in 24 hours, even 8 hours. It can grow because of huge surface area. It interacts with the body fluid and grows much faster, and there is a bone-like morphological growth will be there along the nanofiber surface. Similarly, this is a titanium. This also we studied in back in 2004. So this titanium, when you dip into simulated body fluid, nothing happens. And this sodium titanium, when we do some kind of sodium hydroxide treatment, what we can see here, because of this highly alkaline solution at elevated temperature 65 degrees centigrade for 24 hours, you can see nanowire-like growth on the surface of the titanium, and it's actually there is a nano wires of sodium titanate formation. This sodium titanate acts like a nucleation site, and if you are dipping into simulated body fluid, you can see there is a island-like growth of hydroxy apatite or the mixed calcium phosphate apatite layers. But this is not a continuous layer. And then if we same material, if we dip into bath of calcium and phosphate, alternate bath, saturated calcium and phosphate bath, because of this highly concentrated calcium and phosphate solutions, so they actually promote nucleation on the surface of these nanowires. And then this surface, eventually when you dip into simulated body fluid, has a continuous growth of cauliflower-like structure of bone on the surface of titanium, and it is a quite confluent growth. This is helpful because when you are having a material and you want to have the surface which is helpful for cell adhesion, protein absorption, as well protein absorption and cell adhesion, and also for tissue ingrowth and tissue adhesion, we need to modify the surface of the material. But if we can do in vitro such type of surface modification, basically you benefit in terms of time. So recovery time will be reduced. But so far, people mostly using this kind of calcium phosphate coating on the surface of the material. Not this kind of approach is used for implants so far, but people are working on this. So osseointegration, as I said, it is a biological fixation, and eventually it is the direct anchorage of the implant by the formation of the bony tissue around the implant without growth of fibrous tissue at the bone implant interface. So a process whereby the clinically asymptomatic rigid fixation of alloplastic materials is achieved and is maintained in bone during functional loading. Okay, so I think I'll discuss more in detail. Basically, it should be bonded with the living bone. So for that, we need, as we mentioned, or Professor Gupta mentioned, and Professor Nico also has mentioned, that we need to have highly interconnected porous structure. But is it enough? No, it is not enough. We need, because cells are much. What is the size of the cells? Anybody knows what is the size of the cells? No, not one. It is like if it is fibroblast, it is about 5 micrometer. If it is osteoblast, and it is like 10, 20, 30 micrometer. Okay, so cell has a lamellopodia, philopodia, by which they anchor, and also you have seen today that integrin receptor is bind to the material surface. So that you need to have the material which is rough enough so the cell can anchor and adhere to the surface of the material. Like we are climbing the trees, right? If the trees are very smooth, can we climb easily? No. Similarly, the implant surface has to be rough so that protein can adhere, adsorb. Similarly, cell can adhere by lamellopodias. So we need to have hierarchical porous topography with also hierarchical roughness in the surface, along with interconnected porous structure, so that tissue can grow into it and cell can adhere on the surface of the material, and that eventually causes tissue ungrowth and then tissue ingrowth, where you need the vasculature, 100 micron pore size give you vasculature, and then eventually it gives you biological fixation or osseo integration or osseo incorporation. Osseo incorporation, the term is introduced by Zimmer. So you can see here, in recent time, people are developing the companies. I think this is one of the example where trabecular bone-like structure is introduced by Zimmer. So you can see the cancellous bone, highly porous structure. You can see the trabecular bone, and you can see underneath there is a bone and the titanium at the interface, and you can see at the interface there is a tissue ingrowth. And why we do that? Because we need to have higher volume of interaction between the materials and the tissues, so that the load transfer will be very, very gradual. And there is so to match the modulus mismatch, to reduce the modulus mismatch, so and also for the gradual loading of the from the material side to the implant side, so they use huge amount of open porous structure. And you can see here one of the example, Regenerex, where you can see that soft tissue bonding is also there on the implant side. And interestingly, you can see from the this is also Regenerex, and you can see that bone ingrowth at different time points. In the second week, we can see the 20% bone ingrowth. In 4 weeks, about 60% or 50 to 60% bone ingrowth. 16 weeks, we have about 80% bone ingrowth. And 26 weeks, we have more than 90%, about 80 to 90% bone ingrowth, which is required for biological fixation. And if you do some kind of from microcity studies, this was I think microcity as well as EDX studies of the intersection, they have shown that how the bone ingrowth is there into the porous implants. Okay, and you can see here the average roughness is also a factor. If you have higher roughness, you have higher bone on-growth as well as ingrowth. So you can see the cortical bone has the strength modulus is about 20. I think cortical bone has the modulus of about 20 to 30 GPa, and you can see the cancellous bone has the modulus, I think 0.5 to 1 or 1.2 GPa. So Regenerex has the modulus of about 2 to 3 GPa, and trabecular bone is in the similar range. So you can see that they have so nicely matched the modulus and eventually reduces the stress shielding effect for the Regenerex. This is one of the example where again this is by Zimmer, they have introduced this kind of dental implant where they have about 0.5 to 1 millimeter of porous thickness, where porosity is about 70% porosity, and this is more than enough to increase the surface area of about 90%, and eventually gives the tissue ingrowth and biological fixation to the of the implant to the tissue site. And you can see from microcity that there is a tissue ingrowth to the implants. So here is the EDX studies. You can see that the bright portion is about the white portion is actually metal material, and the dark portion is actually dark area is actually resin block, and the gray portion is actually bone. And you can see clearly that how the tissue ingrowth has happened. So this is studied by EDX. Now, similarly, by histological studies by hematoxylin staining, you can see that there is a tissue, the cell activities and the collagen deposition on the surface of the material. So here is the cartoon for the porous implants, and you can see how the what you call the bone ingrowth is there into the implant surface, and you can see here the very nice bone ingrowth into the porous cancellous like structure of the implants. And this is one of the implant currently marketing from 2013 onwards for dental roots by the GMR. So this is one of the example of mandible. This mandible was introduced, or rather implanted in 2012 to a Belgium lady. She is about 82 years old, and this implant was developed by 3D printing or SLS. Okay, and then this is a titanium implant, and you can see on the surface hydroxyapatite is coated on the surface for bioactivation. But eventually this is so hydroxyapatite is coated, but now, as I have shown through osteoconduction studies, that if you can develop the surface chemistry and roughness in a way that it can also help bone formation on the surface of the material. So this is some of the recent design. I think this design you have taken from within lab, and you can see how the femoral head already. I think a lot of discussion was there. I'm not going into the detail of that. And you see the mandible. This mandible is quite heavy, and you can see the mandible. This will be the feature of the mandible design, where you have inside cancellous-like structure. Even you have a knee tibial tray, it also have a cancellous-like structure where you can have tissue ingrowth and biological fixation for better integration. So this is one of the report by Cisnero et al. So current implant or current injury or trauma is treated using a bone graft. So their bone was taken from either allograft. I think usually homograft is taken from different side, and then it is the clinician who does this wonderful job, but it's a very hard time for the clinician, because as you know that the fitting is a problem. So in recent time, now people are working on customized design and manufacturing. I already, Professor Gupta has mentioned that CT imaging and image extraction using thematics or simpleware or some other softwares, and then extraction of the image of exact size and shape, and then formation of the product, which we will discuss later on. So here you can see this will be the future, but this implant report says that they have used the hydroxyapatite lattice-like structure, and they have shown that this implant did not have enough tissue ingrowth due to unknown reason, because the implant, if the implant size is too big, it is very difficult for tissue ingrowth into the interior of the implants. So that is a major challenge, even still now people are facing, and that is where the role of live tissue printing or live cell printing is another area is coming up. So as you see that this is a XRD studies of bone, dentin and enamel. What you can see, bone is highly crystalline, even dentin also highly crystalline, enamel is also highly crystalline, but you can see the degree of crystallinity for enamel is much higher than dentin and the bone. So as we know that, I think enamel is one of the hardest tissue or the most elastic tissue in the body, most elastic tissue in the body, whereas the soft tissue, skin as well as the vitreous humor and synovial fluids are more viscous fluid in the body. And eventually all these materials has differential viscoelastic properties. So whenever we go for the materials, we will see the huge range of materials are there. They have many different viscoelastic properties and the mechanical properties. So we need, our job is to choose the right material for the right job. So what we can see here, dentin has the elastic modulus 15 to 20 GPa. Cortical bone has the modulus of 7 to 30 GPa, and the compressive strength is 100 to 230 MPa. Whereas cancellous bone has the elastic modulus about 400 MPa. The tensile strength is about 7.4 MPa. The skin has elastic modulus is about 0.1 to 0.2 MPa. Tensile strength is about 7.6 MPa. Similarly, you can see the different tissues like brain, liver, and tendon and ligament. All these different tissues has different modulus. Similarly, the cells. So eventually, the cells specific to the extracellular matrix has their own responses, respective responses. For example, you see the fibroblast has the elastic modulus of 0.5 to 40 kPa, while osteoblast has 25 to 40 kPa. So scientists have shown that by changing the elastic modulus of the material, same cells can be differentiated into different lineages. So I am taking a cell, stem cells, and I am able to differentiate into fibroblast and osteoblast like structure by morphology and the property phenotype just by changing the modulus. So eventually the material's modulus is important for specific tissue type formation or replacement of the specific tissue type. So extracellular matrix is a very, very important component of the tissues, right? So extracellular matrix has very, very diverse compositions depending on the tissue type, and it is the matrix which is other than the cells which are there in the body. And as you know, the bone is a reservoir for minerals, which is calcium and phosphate. Besides mechanical properties, but also it acts as a major role for pH maintenance. Okay, so wherever the pH to maintain the pH of the body environment, it actually helps. It plays a major role. For example, in the oral cavity, you have the dentures. Dentures also is a source of mineral. So in the body, in the oral cavity, when you drink different type of drinks, beverages, and depending on the pH, so oral cavity adjusted the pH by calcium and phosphate, usually the calcium loss or calcium ions dissolutions. So as you know that if you take the orange juice, the pH is much lower, and then a lot of calcium loss will be there, right? So that is why the mineral, the calcium phosphate actually maintain or play the active role for pH maintenance. So it has a diverse composition and nature. It support, segregate the tissues, and also regulate the extracellular, intercellular communication. It regulates intercellular communication. It also regulates the dynamic behavior of the cells. Okay, it also regulates the dynamic behavior of the cells. It also sequesters the wide range of cellular growth factors, and the storage changes in physiological condition can trigger the protease activities that cause the local release of such stores. And of course, it allows the rapid local growth factor activation, delivery, and cell function. So as I said, when we develop the material, if the material is good enough for cell adhesion and differentiation into specific cell lineage, cell starts synthesizing its own extracellular matrix, and these extracellular matrix actually deposit on the side, and then eventually cells start adhering on the extracellular matrix as well, and the cellular activity increases. So that is where we need to have the cells which can adhere and then start depositing their own extracellular matrix. And also, so there are different components of extracellular matrix. One is collagen, which is, I think, the most important molecule. How many collagens are there? Anybody knows, doctors? There are 29 types of collagen. So collagen 1 is one type which is the major abundant in the human body or specifically in the bone. And you see the cartilage, we have collagen 2. If you see the skin, we have collagen 4, collagen 7. So there are different type of collagens are at different tissues. Similarly, the fibronectins, integrin, we know that integrin is also a very important molecule. Elastin, laminin. Laminin is very, very important molecule which is abundant in basement membrane. Tennessine is also important protein component matrix. These all matrix are eventually helpful for cell adhesion also. So proteoglycans like heparan sulfate, chondroitin sulfate, keratan sulfate, hyaluronic acid, these are also components. You can see this is a collagen molecule and different GAGs, glycosaminoglycan, hyaluronic acid, keratosulfate, chondroitin sulfate, okay. And there are different type of proteoglycans and glycoproteins which are there as a component of extracellular matrix. And this all these matrices has their own role, an important role. This is one of the cartoons of basement membrane, and you can see here this is the laminin. And later on we will show you that laminin acts as a nucleation, acts as an adhesion site not only for cells but also for GAGs, proteins, and so on. So you can see the laminin here, and you can have collagen 4. Collagen 4 is a mesh-like structure, and basement membrane is actually limiting membrane for the blood vessels. So in the skin, you have basement membrane. Beyond that, there is a keratinocyte layers. So above the basement membrane, there is no blood vessels. So basement membrane acts like a limiting membrane, and then basement membrane to connective tissues, there is a stitching by the collagen 7, which is another important molecule. And we know that there are intercellular connections. There are intercellular connections as well. So there are cell-cell junction, I said. So and cell-cell junction is mostly there are different type of tight junctions, different type of gap junctions, which is a channel for exchange of the molecules, and also there are cell-to-cell junctions is also there. As I said, in case of basement membrane or in case of epidermis, the cell is adhering to the cells by equiadherent junctions. Okay. And very importantly, you see the cells membrane. This is a cell membrane. So as you see that there is a phospholipid bilayers on the surface of the cells. So this cell surface has a charge. This cell surface has charge, and this is highly negatively charged. So now if you have a material which we want to use it for biological application, if I want very high cellular activity, eventually I want that the material should actively participate in role of cell adhesion. So how you can adhere more number of cells into the material? Simply, if I have a positively charged surface, so what we can do, we can take a polyol lysine as a material which you can coat on the surface, and at pH 7.4 it is highly positively charged. And simply these materials, this is a material which is used for packaging. You know, this material is used for packaging. You know, when you purchase a computer, when you purchase for a computer, the packaging material is there, polystyrene. The same material is used, but the same material is used for cell adhesion studies. But this material can be coated with polyol lysine. Polyol lysine, when it is coated, it is highly positively charged, and then cell is highly negatively charged. Eventually, there is electrostatic interaction, and cell will adhere to the surface. Okay. And similarly, can you use any other material? Can you propose anything? Collagen, for example. Collagen has RGDs. Sorry, collagen has RGDs. Yes, arginine, glycine, and aspartic acid. This arginine is recognized by the cell surface receptor integrin. So simply collagen can be coated. So in the market, very different type of cell culture these petri discs are available. Some of them are polylysine coated, some of them are collagen coated material, which eventually promote cell adhesion by either by RGD receptor or by electrostatic interaction, and then we can expand the cells on the material surface. Okay, so definitely surface charge is important. Surface charge is important. I think I want to stop here. I'd like to acknowledge different figures and tables we have taken from different papers or different notes, okay, or different note pages. So I think this is solely for teaching purposes. It is not, there is no commercial value for it. Okay, thank you.